Hi, everyone. My name is Kuwei Q, and I am a software engineer at Facebook. Today, I want to talk about GraphQL error handling done right. It is the way to increase engineer productivity and let users get the most out of the product. So this is the agenda for today. First, we're going to talk about an experimental feature that we have been working on at Facebook called @required that introduces error criticality. Second, we're going to talk about effective error reporting with machine learning. And lastly, we want to introduce some creative triaging leveraging GraphQL schema information. So before we jump in, I want to briefly mention the GraphQL support structure at Facebook. So we have many different products across the Facebook and Instagram ecosystems that uses GraphQL as the data fetch framework that gets the data from the web servers. However, on the other side, in the infrastructure side, we only have a handful of teams that supports the core GraphQL infrastructure. It is our GraphQL server team, GraphQL mobile client, web client, and a GraphQL foundation teams that kind of look at the GraphQL ecosystem across the board and find out ways to optimize things. So one of the challenges we have always been facing is how does this handful of core infrastructure teams scale their support to many different products? How do we make changes that improves the GraphQL ergonomics? And how do we increase the developer productivities for all these product teams? So I hope with today's topic on error handling, I can show you some of the ways Facebook is doing it. So first, let's talk about error criticality with @required. So first, let's recall the GraphQL errors defined in the spec. So the errors entry in the response is a non-empty list of errors. It means that errors do not have priorities. So that list of errors is not ordered by the importance of each error. And the second thing is that errors actually have very limited effects on the final response. So if it is a nullable resolver that has errors, then the field will just become null. And if the resolver is non-nullable, we actually bubbles up the null until it reaches a nullable ancestor. So the way it affects the final response is pretty limited. So here is what @required does. @required is essentially a field level directive that you can annotate on any field inside a query or a fragment. @required brings non-null to the client. And here we're just talking about a client that can generate some typed response models based on the query structure. Any field you annotated with @required will become non-nullable in the generated type for your response. And the field's required status is local to the fragment where it is specified. So for example, if I have another fragment for this query that also fetches the name field, but without the @required directive, the name is still going to be non-nullable for my user fragment, but will become nullable for the other fragment. And lastly, this is for the server side. If a required field becomes null due to the server exceptions, the exception is logged with the highest level of criticality. So why do we need @required? In a GraphQL schema, we already annotate whether a field is nullable or not. What we found is that data requirements is essentially a product decision. So here I want to show you an example with the marketplace, your offer component. The price information here is absolutely required. There's no way you're going to render the your offer component in any meaningful way if you do not have the price information. However, the price information may not be necessary if you're just rendering a list of catalog that's currently available. Second, the error criticality should align with the end product's perspective. So I'll give you an example of what this means. So let's say we have a component that's trying to render, and here are the server-side exceptions without the end product's perspective. So the first exception is connection exception already connected. Looking at this, you might be saying, okay, this is not ideal, but we're still connected, so we're all good. The second exception is timeout exception. And looking at this, you would say, yeah, this is not good, but timeout happens from time to time. All we need to do is retry. And the last exception is invalid token. Looking at this, you might be saying, well, it actually means there might be some bugs in our code, and we should prioritize in fixing it. So you would prioritize invalid token first, connection timeout second, and already connected third. And let's take a look at what's happening on the client side from the end product's perspective. So what we're trying to do is we're actually trying to render a user profile page. It has the current user's profile picture and the list of friends' profile picture. And this view is backed by the GraphQL core user profile that has these two profile picture fields. And looking at this, you would say that, well, the profile picture for the current user is much more important than the profile picture for the list of friends, because if one of the friends' profile picture fails to render, then we can just simply drop it from the list. With @required, you're going to annotate the viewer's profile picture was required. And then here you introduce the error criticality. And with that, further investigating it, you find that, well, the viewer's profile picture errors out mostly due to timeouts, and the friend's profile pictures errors out due to invalid token. So here you actually reach a different conclusion of, okay, I actually should prioritize timeouts. And later on, with some debugging, you find out, okay, timeouts happens when the user is traveling to a different area where they're hitting a data center that the cache is not hot, and you can do something about it. So here with the end user's perspective, the product team can actually prioritize the most important bugs first. So criticality allows developers to prioritize the most important bugs first. And what we're saying is @required brought together data requirements with exception criticality and allow developers to focus on the most important things first. Second, let's talk about effective error reporting with machine learning. So now that you have all the raw logs for your GraphQL errors, so this is actually a real screenshot of Facebook's error logging for GraphQL. And because these error messages and error paths are considered confidential information, I cannot really show the real content to you, but you get the idea. You know, we log something like the operation name, exception class, exception messages, et cetera, et cetera. So what you need to do is take these raw logs and turn them into a time series. And with the time series, you're going to be able to find out the spikes and start alerting on them. So to turn all the raw logs into a time series, what we essentially do is a group by operation. So initially what we did is, well, we're going to group by operation name and exception type. And this is what happened. So we run into something called massive overaggregation. By overaggregation, what I mean is a group actually contains multiple different root causes. So let's say the group by the operation name is fetch user information and exception type is null pointer exception. And so within that query, there might be different resolvers that have null pointer exceptions due to different root causes. And the problem it brings is it's actually impossible to triage that alert or that task to a specific engineer, because you actually need several different engineers that addresses the different root causes. So we changed our strategy to, okay, maybe we should introduce error paths along our group by information. And what we find is then we run into under aggregation. By under aggregation, what I mean is that you may have several different groups and all of them are caused by the same root cause. And the problem under aggregation brings is that the alerts are not triggered because now one root cause is separated into several groups. Each group's volume actually drops and you're not hitting the threshold that triggers the alarm. So we tried out all kinds of other strategies. Some improve the situation, others don't. And if you are in a different company and using different patterns, the error path might actually work for you. So what we find out is that we actually need a metric that kind of informs us which mechanism works better and which mechanism doesn't work. And this is where machine learning comes into place. So first, we introduced a metric for over-aggregation using string distance-based machine learning model. So what we do is within each group, we analyze the stack traces and error messages and then compute the string distance for these stack traces. And we call this the cohesion score. So if within a group, the stack traces and error messages looks very similar, the cohesion score is going to be high. And it also means that it's less likely to be over-aggregated. And on the other hand, if your cohesion score is low, it means the stack traces actually looks pretty different. The chances are you are over-aggregated. Next, we actually introduced human auditing into the process and find out the threshold that determines whether a group is over-aggregated or not. So for example, we decided, okay, 0.84 is the threshold for over-aggregation. And any group that is under that threshold is considered over-aggregated. And here you can actually compute that metric for how many groups are over-aggregated. Next, we introduced the under-aggregation metrics using the clustering-based ML models. So what we are doing is each group is a point in a space, and we're trying to cluster them based on the distance as well. So to compute your under-aggregation score, what we did is how many groups do we have based on the current group by strategy, and how many ideal groups should there be based on the machine learning clustering? And there you compute that under aggregation score. So with both over aggregation and under aggregation, we're able to iterate pretty fast and try out many different strategies and get feedbacks from them. And we actually find out a really good strategy that allows us to group these errors by and then triage them effectively. So some of you might be asking, so why don't you just replace this group by mechanism with the machine learning models directly? So this is actually another lessons we learned, is that for these error reporting, you want to be able to find something that is deterministic. So ML models are not, right? They're able to change overnight. And second, you want to be able to explain why a task is fired and triaged to someone. And the machine learning model is more like a black box that you cannot explain. So what we're saying is ML models informs us to move in the correct direction and allows us to improve the error reporting with confidence. Lastly, I want to talk about some creative triaging leverages GraphQL schema information. And to talk about this, I have to talk about OOMs and timeouts. Based on our experience, OOMs and timeouts are the most difficult errors to triage. The reason is that there could be many different stack frames for the same underlying issue. So say that a OOM tends to happen in a certain area of functions, but the exact stack trace may vary a lot. So your traditional stack-based triaging algorithm may not work very well. What we actually need is a coarser granularity to identify the problem. And here is how GraphQL schema information help us to achieve that. So what we actually did is we annotate the stack frame with the GraphQL schema information. So here you can see that this is a stack trace, and for the functions that are returning a GraphQL type, we annotate that. For the function that are actually executing the GraphQL field, we also annotate that. For some infrastructures, you may not be able to annotate the stack frames, but you are able to, log something along the way of, what is the current path that I'm executing and achieve a similar result. So what we do with this information is we collapse the stack trace. So this is the same stack trace, but it's colored, where the highlighted color is your GraphQL schema information and everything else is grayed out. And you collapse this stack trace into the GraphQL stack trace. So with this stack trace, you can actually inspect it pretty easily using human eyes. You can identify, okay, so where is my on timeout centered around? Is it a specific GraphQL object or a specific GraphQL field? And find out what is going on wrong. And even better, you can actually still reuse your stack-based triaging algorithm, but instead of using it on function stack traces, you're using it on GraphQL stack traces. So the takeaway for this talk is that we want to define error criticality from the user's perspective. We want to make informed improvement with metrics, and ML can be a really good one. And lastly, we should leverage GraphQL schemas as metadata whenever we can. So thank you very much. And if you have any questions, don't hesitate to reach out.
Excellent talk. Thank you so much for that. Again, my synapses are firing like crazy, and I have a few questions for you. When you were working through all of this, the error criticality and all of that, how do you determine and introduce error criticality if you don't have anything up front? Like, how do you make the signals remain critical over time?
Yeah, so what happens is when you're defining a critical error, you're also defining what's your expectations for the team who will be receiving those errors and are responsible for fixing them. So basically at Facebook, this is not GraphQL specific, but we find it work really well, is that we introduce a concept of on break now. And we have a specific expectation that you're able to solve it within 24 hours. And if you're not, there is this 7-day escalation period. And so that's the standard that we first created so that when people are receiving, they're seeing, this is a critical GraphQL error. That means I have a task that is literally, I have to unbreak now. So by introducing those kind of escalation policies along with your error criticality, you kind of, people know what's the effect of this error. It's just not another name that you're introducing. We used to have, we tried a lot of things coming up with names that just try to help people to prioritize must fixes. And if you don't have those escalation policies along with them, people are just going to ignore them. And then the second question is about how do we make those signals critical along the way, right? All the time. So when you introduce a signal, that is going to be critical. And gradually there are going to be noises creeping in, and over time you lose that signal of criticality. So what we did is we actually, we come up with what is called the reliability program for those product teams that are using GraphQL. So a lot of times people are I have this GraphQL, I sometimes have errors and sometimes not. Like, how do we come up with a standard metric that evaluates your reliability of or your like error handling of your product? And we come up with those programs. And the criticality is a signal that's with that is used in those programs. And we give them a standard of how do you evaluate your reliability. And teams like adopt that. And because it is like globally introduced among like all the teams using GraphQL in Facebook, so people are motivated to continue to fix things. Like even though it's noise, sometimes it's noise, they would still be motivated because it's like a standard program that everyone just follows that standard. Yeah,
I got you. So set standards, and then those will be followed. So, and I guess if there's a certain saturation point with errors or something, it's up to the teams to manage that level and to decrease the rate of errors if they're being oversaturated or something with errors.
Yeah, so we actually define those standards. Like we're saying basically you cannot have critical error over 10%. And if it does, like we create what is called a major site event for them, because like we actually collect some historic data on like those GraphQL errors and how they're affecting our end product. And we have that number. And we're saying, okay, even though this is a noise for you, but you should keep it critical so that in the future we can still use these signals effectively.
Gotcha. Yeah, that makes sense. So one of the other questions come up a little later in your talk. I noticed some you were going through some machine learning practices that you were using. Yeah. And I was curious what the features for the ML for under aggregation were.
Yeah, that's a great question. So for over aggregation, I think in my talk, I mentioned we're just using string distance based models so that, stack traces look similar, then, or if they look different, we would split them. For under aggregation, part of it is actually similar. We also use stack trace based this string distance based models so that if you have two groups that should be merged together, that helps. In addition to that, we actually find some other signals, other features that are super effective. So one is how similar is your timeline series. So if two groups are actually supposed to be one, then their spike patterns look very similar. They usually happen around the same time with the same level of increase and then drop and things like that. So that is one of the features that we find useful for under aggregation. The other feature that we find useful is, so I think there are other terms in other companies when you land a code review. At Facebook, we call that a diff. So you land that into master, and there is a number associated with that. So what we do is, okay, based on this stack trace, who should I or which diff should I be triaging to? And if two different groups are triaged to the same diff, then that is also a great feature for deciding that they should be merged together, meaning they are under aggregated.
Gotcha. Very interesting. Well, thank you very much for that talk, and thank you for answering my questions. Appreciate it very much.
Thanks.